Hi, this is section 6.1 about angles. This is actually the beginning of trigonometry in pre-calculus. And so we're going to introduce a lot of concepts. Most likely those concepts should be familiar to most of you, but it's good to review all of them. We first start, when we talk about angles here, first thing I want to introduce the letters that we use the most in trig. Those are Greek letters. Alpha is one of them. Alpha, beta, beta, gamma, and we have theta, and then we have omega. Those are Greek letters. We're going to be using those letters throughout the course. The first thing, because we're talking about angles, we are going to draw a line. This line I'm going to call the initial side. And let's say I draw an angle like this. This is the angle I'm going to draw, call it alpha. This is called terminal side. This is called terminal side. And what we need to do here is this direction I drew the angle, that's called counterclockwise. Which this is always going to be the positive direction. If we go the other direction, that's the clockwise direction. And that's going to be the negative one. So if I want to draw an angle like 60 degrees or something, how do we draw a 60-degree angle? So you draw an initial side and you kind of estimated this is 60 degrees. If I want to draw a different angle, let's say I want to draw negative 180 degrees. So how do I draw this? That's the initial side, so it's going to go this way. It's negative 180 degrees. What about if I want to draw a bigger angle? Let's say 400 degrees. How do I draw this angle here? So we define, when you go in one full cycle, we call it one revolution. Each one revolution is counted as 360 degrees. And we can use this to start constructing the 400 degrees. So how do we start with the 400 degrees? I'm gonna start here. I know I'm gonna go 360, but then on top of that, to make it 400, I need to add 40 more. So say this. So this means the angle I'm looking for is started here and terminated at this line. So this is the 400 degrees. The one in green. Now, when we do length, like measure the length of an object, there's so many ways to use different units. It could be like in feet, in inches, yards, centimeters, millimeters, meters. Same thing with angles. We use 3 different measures. We need 2 of them only in this course. One is the degree measure that we use most of the time, and the other one is the radians. So 1 radian is defined as if we have a circular path like this with radius r, center O, and this is the length of this arc subtending this angle here is called central angle is r. So this angle here is 1 radians. And radians is abbreviated with RDS or RD, 1 radians. So what's the relation between these degrees and radians? We'll see that in a minute after we go over this arc length, so the length of that arc. So if we have draw another circle here and circle center that O, radius R, and let's say someone traveled on this arc AB has a length the length of arc AB is S. So by definition, if I call this angle theta, we have S is equal R times theta. S equals R times theta. This theta must be in radians. Theta must be in radians. So how do we apply this to an example first? So let's say find an arc length of an arc on a circle with radius 4 centimeters subtended by a central angle of 0.35 radians. So to do that, they're asking about the arc length. So we need to write the formula S equals R theta. They give us the radius 4 centimeters, and then times the theta. This theta has to be in radians, which they already gave it to us as 0.35. And if we multiply that out, 0.71.4 and centimeters. So the unit for S matches the unit with the radius. Whatever the unit of the radius matches with the unit of the arc length. Now, what's the relation between degrees and radians? The relation between degrees and radians. So if we take the formula we have earlier, S equals R theta, we know from before the length of the entire circle, which we call the circumference, has a length of 2 pi r, where r is the radius of the circle. So if we substitute that in here, 2 pi r equals r theta, we can drop or divide by r. So theta, which is the center angle here, in this case is a full circle, it's 2 pi. So that means that 360 degrees is equivalent to 2 pi radians. So good to know that 180 degrees is pi radians. So how we're going to use this? This would help us to do conversion from degrees to radians and vice versa. So if I want to do some examples on this, so if you want to convert something from degrees to radians, what do? We take that degrees and multiply it by pi over 180 degrees. So the degree will cancel each other, and that will leave things in terms of radians. So always from degrees to radians, multiply by pi over 180. Now from radians to degrees, multiply by 180 over pi. Example on this, convert. Let's say we have 60 degrees. How do we convert 60 degrees into radians? Well, we multiply by pi over 180. And the zeros cancel, so that gives 6 pi over 18, which is pi over 3 radians. So 60 degrees is pi over 3 radians. What about if we have 720 degrees? Again, we multiply the 720 by pi over 180. The zeros will cancel, and then if we reduce this out, that's 4 pi radians. 4 pi radians. What about vice versa? If they ask us to convert, let's say, 2 pi over 3 radians into degrees. So we take the 2 pi over 3 and multiply it by 180 over pi. So the pi's will cancel, and that will give us by 1 by 360, 120 degrees. So 2 pi over 3 radians is equivalent to 120 degrees. Another application here, beside the arc length, is to find the area. So if we have a circle like this, radius r, angle theta, and we can find the area of the shaded sector. So this theta is the central angle here, central angle, and r is the radius of the circle. To find the area of the sector, it's we use 1/2 r squared times theta. Theta must be in radians. Theta in radians. So if we are asked to find, let's say we're given this, and radius 6 centimeters, and let's call this 60 degrees. We need to find the area of the shaded sector, this shaded sector. So the area is 1/2 r squared theta. One thing to note here, theta is 60 degrees. So we have to convert it. If you convert to radians, which we did earlier, was pi over 3 radians. So this is 1/2, r is 6 squared, and times pi over 3. So that gives us 1/2 times 36 times pi over 3. So which simplifies down to 6 pi. cm squared. You can leave answers in terms of pi, or you can just multiply it if you like. What can be other applications to this? We can look at, assume we know from before that rate is distance over time. Now here we have a central angle O. We get an object moving from point A to point B on this circular path. So we would like to know the velocity of the object on this path from A to B. How fast is this moving? Say the length of this arc is S. We define it similar to r equals d over t. In this case we call velocity, and the distance here is s divided by the time t, where s is the distance traveled along the circular path, and t is the time. V is the velocity. We call it linear velocity. So now note something. While the object is moving, so let's say the object is somewhere here, so the angle that this object kind of formed is this, and then again this angle is changing all the way to get to B. So let's call this angle here theta, the whole thing. This angle is changing. So what we can find for this, we can find how fast this angle is changing. And this is called angular speed. We use omega for that. It's called angular speed. So it measures how fast the angle is changing as the object traveling on the circular path from A to B. And what is it defined as? This is defined as the center angle that we have divided by t. Keep in mind, theta has to be in radians. Now, if we take these boxed formulas, V equals S over T, and we know S has a formula R theta over T, and notice if we group these together, that's omega. That gives us a relation between V and omega. The velocity, the linear velocity, is the radius times the angular velocity. And usually the unit of omega is radians per the unit time. per the unit time. One quick note, one revolution is 2 pi radians. Keep that in mind. So if we have, let's say, they give us, ask us to convert 120 revolutions per minute, RPM abbreviation, into radians per minute. So the way this is done, I write that down. Units are important. Revolution per minute, it's given. So what do we need? I need to get rid of the revolution. So I write 1 revolution here is 2 pi radians. So notice the revolution cancel out, and we get 240 pi radians per minute. And to look at an example how to find the linear and angular velocity, let's look at this example. An object is traveling along a circular path with radius of 2 meters. If in 20 seconds the object travels 5 meters, what is its v, the angular linear velocity, and omega, the angular velocity? So let's write down what is given. The radius is 2 meters given. They give us the time, 20 seconds, and they give us the length of the path, which is 5 meters. We would like to find V. V is defined as S over T. S is given 5 and T is 20. So that's 1/4 meters per second. We need omega. Omega has 2 formulas. Either you can do theta over T, but theta is not given, so, or we try the V equals R omega. V is 1/4, R is 2, omega. If we divide both sides by 2, that becomes 1/8. So we got omega to be 1/8 as an answer. So this is the linear, one of them the linear speed, and the other one is the angular speed. That was basically introduction to trig, and so we can, if you want to finalize this, that's radians per second. This is section 6.1.